All right, thanks a lot for the opportunity to give an overview of some of the exciting work being done at the interface between collider physics and scattering amplitudes. And a special shout out to Winter Storm Oakley for providing me with a captive audience of East Coast attendees this morning. So as usual, like many other speakers, I can't cover everything in this time period, and this isn't really a comprehensive review, but just some selected topics of things I think are interesting and where things may go in the future. Now, if you talk to a bunch of amplitude physicists, they don't even know what they mean by an amplitude. So here's the blindfolded scientists encountering the elephant and trying to, different ones will have different interpretations of what amplitudes are or what are the important things to do in amplitudes. Like Svi over there might see two tusks and think it must be a double copy of some kind. Or Nima listening in from Princeton might think that this broad back is a polytope and so on. So there's a broad community of people, and I'm subject to my own limitations and only covering some of the things, but part of the charge was to try to connect it a little bit to what's measured in experiments. And amplitudes, again, it connects with many different areas of both physics and mathematics. And you can see ranging from things like fluids, it's been discussed in that context, to chiral perturbation theory. There are connections and stuff I've been doing, say a little bit about with integrability. And so there's connections to both experiment of various types and also, say, experimental mathematics. Fortunately, I don't have to cover all this because we're going to have 3 great talks after me. And Mikhail will talk about the connections to classical gravity, Henrietta about effective field theories, possibly SNEFT or chiral perturbation theory, and Nima maybe more on the side of polytopes, algebraic geometry, things like that. So I'll focus on sort of connections to collider physics and mostly QCD. Now, there's sort of one theme that I think a lot of amplitudes researchers have as a kind of working philosophy, which is you find a way to compute something that hasn't been computed before. You stare at it and try to understand the patterns or principles that might be behind it. And then you try to use those principles to invent better algorithms so you can compute to higher orders, so you can see more patterns, so you can, and so on. So that's sort of Amplitude's virtuous circle. At least I remember John Joseph describing this, but I think a lot of other people have think about things this way too. Now, on the collider physics side, I'm going to focus this talk on precision collider theory. There are definitely other ways that there's contact between collider physics and amplitudes. For example, SNEFT that I mentioned briefly. There are things there, there's a white paper on that. But on the precision side, the challenges are that there's not just like one process at the LHC. There's dozens and hundreds of processes that are being measured by experimentalists at increasingly high precision, but different precision for different processes. And there's a range of sort of degrees of difficulty. It's probably obvious to everybody if you add more loops, that's harder. If you add more legs or higher multiplicity, more objects in the final state, that's harder. If you add more masses to the internal lines, that turns out to be harder too. The functions get more complicated. If you have more partons and jets in the final state than like W bosons, that's also harder for different reasons. So, and also like total cross sections are easier, and they're usually the first thing that you calculated to give at the next loop order, but they're never actually measured because of experimental acceptance cuts. So then you have to work to get more differential, and that often is much harder. Also, we're not so fortunate that we can always do things at fixed order. Resummation is needed in many corners of phase space. For example, soft gluon emission, there's a set of resummations built up around that also interacts with a lot of the fixed order techniques, but that's a little different direction. So also, you know, sometimes what experimentalists can measure is dictated by other physics. For example, they have to make very severe cuts on B jets additional B-jets when they measure WW, because TT bar produces WW in abundance with B-jets around, things like that. By the way, there's a recent review from 2020 by Gudrun Heinrich on a lot of these aspects. So this is another way of seeing the challenges. This is just some small subset of all the things that have been measured by Atlas in this case, and of course a similar plot from CMS. And they range from standard candle type processes like W's and Z's through tops, through many body things, many final states. And you can look over here and see the wide range of cross sections, which often dictate the statistical errors. These processes are very tiny cross sections, large statistical errors, but they're going to come down by a factor of 5 to 6 or more through the end of the last high luminosity LHC runs. And you can see that the theoretical error bands are smaller, but not always smaller by that much, so there can be more work to do. You'll notice that these bands are broader than these, and there are 3 bodies in the final state, and that's not a coincidence, as we'll come back to. So just one landmark example is the total cross-section for producing the Higgs boson at the LHC via gluon fusion. To get to high precision, we have to integrate out the top quark and replace it by an operator, which is essentially the Lagrangian, a product of 2 gluon field strengths. And then after integrating that out, we save ourselves a loop in here. And then people like Bernard and his collaborators have been able to push this all the way to n cubed LO, which is this thin band here. And you see that at this point it's becoming quite precise. And at the total cross-section level, probably close to adequate for what's needed for the HL LHC. But of course, it has to be made more differential ideally, and that's part of the path towards N3LO that Bernard talked about yesterday. And so often, though, LO is just a really lousy guide, and NLO starts to make things semi-quantitative. So you have to get to NNLO to start to approach true precision. Just a brief word about what enters these corrections. Well, lots of things enter it that I can't possibly talk about, but one of the building blocks are scattering amplitudes with different numbers of loops and different numbers of legs, even for just a single process like Higgs production, because you can always produce the Higgs in association with more partons or more jets. And when you do it inclusively, you have to add all these contributions in, but you need fewer loops with more legs. So there's a gradation of different problems with different numbers of loops and different numbers of legs. Just as an example, though, this process, which is 3 gluons and 1 Higgs, or 1 operator, is like a 3 gluon form factor. In QCD, the state of the art is 2 loops. And maybe it'll be possible to go to 3 loops before too much longer. So, but these scattering amplitudes are the underlying building blocks. And when you go to the multi-loop level, they often get very complicated and hard to evaluate. And part of it has to do with the difficulties of doing the loop integrals. Back at 1 loop, everything was reducible to one special function, the dilogarithm, along with logarithms. Basically, because everything could be reduced to scalar box integrals when the momenta are in 4 dimensions. But when you go to L loops, you start getting special functions that have many more integrations than just this 1 or 2 integrations, depending on how you count. Anyway, you get up to 2 L integrations at L loops, and there's some analysis that this is the maximum. And these can be weight 2L iterated integrals of special types called multiple polylogarithms, or sometimes worse functions, come back to in a second. So in order to help simplify the problem, we're going to look at a toy theory, which is close to QCD in some ways, but not exactly QCD. And that's planar N equals 4 super Yang-Mills. So it's a maximally supersymmetric cousin of QCD, where the gauge group has a large number of colors. And that gives it an integrability, which tells us we should be able to solve it, but it still doesn't tell us exactly how to solve it. So the structure of the N equals 4 amplitudes is very rigid. We know exactly what's happening with all the rational functions of the kinematics. And we could focus thereby on the transcendental functions, which are often very similar to transcendental functions that show up in the QCD case. And there's also extra properties that allow us to push forward much further in this theory than we can in the case of QCD. And one of them is the ADS-CFT correspondence, which gives us a strong handle of what's happening at very strong Tuft coupling. Also, and not unrelated to ADS-CFT, is a remarkable feature that scattering amplitudes in this theory are dual to closed polygonal light-like Wilson loops, which also gives them an extra symmetry. Very recently, we found another kind of duality that relates at least one amplitude and one form factor, and we think it relates more. And you can use all these things once you accept them and use them to go further and push things to higher loops and more legs and things like that. So just very briefly, QCD has quarks in the fundamental representation of SUNC for NC equals 3. To get N equals 4 super Yang-Mills, we put the quarks in the adjoints and also add 6 real adjoint scalars, and they're all in the same supermultiplet. So N gluon amplitudes are more or less give you all the amplitudes for other particles as well. And the Feynman vertices are not so dissimilar, except for the group theory of this adjoint. This vertex for gluinos is the same as the one for quarks in QCD. So there's lots of similarities. Of course, there's new things like scalars and Yukawas and stuff. But if you're thinking of scattering amplitudes with an arbitrary number of gluons and you're at tree level, the theories are really the same. Because at tree level, if the outside guys are gluons, then everything inside must be a gluon too. You can't use any matter vertices because matter is pair produced, and then you would have to destroy it, and that would make a loop. So there's a close connection at tree level in that all the amplitudes obey all the identities of N equals 4 supersymmetry, and so many amplitudes just vanish because of that. And the simplest ones have a very simple structure, the Park-Taylor amplitudes, and they are very independent of the location of the negative helicities, for example. These are all very simple consequences, but all of this is busted to some extent when you go to the loop level, but not completely. So at the loop level, you find like one loop for this 3 gluon matrix element with the Higgs or some operator. It has some dialogues in it, and they're pretty similar to the ones that appear in QCD. But then the QCD one has sort of simpler functions like single logarithms instead of dilogarithms that come along for the ride as well. So there's some kind of correspondence between N equals 4 and QCD, but they're not exactly the same. More generally, the N equals 4 super Yang-Mills amplitudes at L loops have a kind of uniform weight. At least this is a conjecture of 2L for the finite terms in the amplitude at loop order L. And this weight is just illustrated by one certain subclass of functions, the multiple polylogs, where you keep integrating dt over t to raise the weight all the way up to n for the nth polylog. Now QCD amplitudes, by contrast, they typically populate all the weights from 0, which we call the rational part, all the way up to 2L. So the N equals 4 are a simpler prototype for what we're going to see in QCD when we can get to that level. Now, in some cases, there is an even tighter connection between QCD and N equals 4 because some quantities are gluon dominated. And if they sort of invoke, they can be a multi-loop graph where you're required to have gluons and only gluons. And then for the same reason as at tree level, you get exactly the same results. Here's one example. This is something that characterizes the 1 over epsilon poles of scattering amplitudes, which through 2 loops have only kind of dipole divergences that depend on 2 of the external particles. But at 3 loops, you have quadrupole terms. And these quadrupole terms require you to connect together 4 different partons with a tree-like graph of gluons. You're still integrating over things, but because it's only gluons, It's the same in n equals 4 as in QCD. And so that tells you something about the structure. It tells you that you should expect the answer to be a uniform weight function because of this inheritance from n equals 4. Also, after this was constructed, there was a bootstrap approach. I'll say a little bit more about that. But you can use kind of n equals 4 techniques sometimes in things that are more general than just n equals 4. And there's this very similar story for two-loop where you have a single soft emission. Now, in some cases, even when the objects are not exactly the same in the two theories, they have pieces in common. So the pieces in common before had to do with most complicated color structure. In this case, they're most complicated transcendental structure or maximum weight. The QCD formula for the light-like cusp anomalous dimension, which enters in a key way in soft gluon resummation and infrared divergences and amplitudes, that structure depends on some group theory Casimirs, but then it has some numbers in it. And these blue numbers here, and if you were to go up as far as it's been computed to 4 loops, the most complicated numbers that have the maximum weight are always given exactly by the n equals 4 result. So you can get glimpses of what's going to happen in QCD when you understand the n equals 4 theory. There, in some cases, you can go even further because of the fact that the generic integral topologies are exactly the same. And sometimes when you look at things from an amplitude perspective, you see some things that were kind of lying in plain sight in principle in the QCD case, but because the things are complicated, they weren't really investigated. For example, we've been looking at these Higgs 3-gluon type things in n equals 4 recently, and at 2 loops, the integrals that entered were computed over 20 years ago, and they were a set of polylogs. But we in another group noticed in the course of our investigations that these integrals all had an extra structure. Certain things shouldn't appear next to each other in something called the symbol. And that structure actually holds beyond the integrals that are just responsible for it happening in planar n equals 4, but for all the integrals in QCD. So the fact that the sort of set of integrals is very similar lends more to the interplay between n equals 4 and QCD. This slide just indicates different flowcharts that you might do to use methods you might use to calculating a perturbative amplitude. And the sort of initial way to do it was to draw all the Feynman graphs, evaluate all the Feynman rules, and then perform all the integrations over the loop momenta. So you might get a sum like this where it's labeled by different Feynman diagrams. And then it was noticed that another way of organizing the integrand was by calculating unitarity cuts in different channels and using that to build an integrand, not by individual Feynman diagrams. But at the end of the day, you still have to perform all of the loop integrations. And so you get a slightly different organization. And that's been used a lot in n equals 4 and n equals 8 supergravity, for example. And also it's becoming very popular for QCD when you have more and more scales in the problem. And the diagrams have much more sort of cancellations between them and so on. But another method is to just guess the answer by writing down a linear combination of functions. The functions in the end should be related to these integrals, but you don't know exactly what the relation is. And you just solve for some rational numbers. So we call that the amplitude bootstrap, and it works extremely well in planar n equals 4, where we have a lot of boundary data to fix all these constants. But then, of course, you can study things and go between different pictures. So as a result of a large amount of work using principles that Nima might touch on more in the next talk, there's sort of an understanding of the kind of functions that enter scattering amplitudes for a general number of external legs in the case of planar n equals 4 Super-Yang-Mills theory. And when you're at small numbers of legs, everything is multiple polylogarithms. In fact, there's a symmetry that sort of tells you that everything is just numbers called multiple zeta values at the 4 and 5 point level, and you only start getting interesting stuff at the 6 point level. And using knowledge about the multiple polylogarithms, you can push to 7 loops in the 6-point case and 4 loops in the 7-point case. And there's other principles that allowed the computation recently of 8-point MHV to 3 loops. And then past this point, we don't have complete amplitudes, but we have a lot of understanding of some of the integrals, and they start to go beyond the multiple polylog class to more complicated functions. Thanks. So multiple polylogs, or G functions, is one description of them, are given iteratively by integrating a previous one, dt over t, minus some constant, which could depend on the external kinematics. And you can also define them differentially so that the derivatives have a restricted format, which is a sum over a finite number of differentials of logarithms called the symbol alphabet. I didn't say it here, but these are the letters in the symbol alphabet. So they start to get more and more numerous as you go to larger numbers of legs. And some functions aren't even in the multiple polylogarithm class. They are starting off, going beyond that class, you tend to get elliptic polylogarithms where the singularities are on elliptic curves. So these elliptic polylogs are important in phenomenology because they enter things much earlier when you have massive internal lines like top quark processes, and Bernard mentioned them briefly yesterday, or electroweak corrections with masses tend to bring these in principle. So you can also study the cases of multi-scale elliptic polylogs in processes or integrals that you need for planar N equals 4. So there's been a lot of work done on that over the years. And people have gone further to study more complicated surfaces like K3, Calabi-Yau's, banana diagrams. Thanks. So there was a revolution in the number of processes that could be done at next to leading order around the 2012 to 2017 time period. Many processes that have 2 bodies in the final state were pushed to N and LO, largely because of appreciation, understanding, and implementation of these G functions for the virtual parts. Some of these also were elliptic. But the progress since 2017 on the N squared LO, the N and LO frontier, has been to push to 3 guys in the final state. And the bottlenecks are partly these loop amplitudes. And so there's been a number of very nice computations of these recently in using unitarity. And they're still in the multiple polylog class, but they're still much more complicated functions than 2 to 2. Also, even here, there's been in the gamma, gamma, gamma case, N and LO. This is a case where the results shift enormously from leading order to next leading order to next leading order. And they're now approaching the data from, I think, Atlas here. There's also been more work, even more recently, too numerous to mention, including one massive leg and some of the non-planar configurations besides leading color. And all of this has been incorporated into the N and LO contribution to 3-jet production in a recent paper from last year by Chacon, Mitov, and Poncelet. And this is a very nice application. You see, when you see a huge jump from LO to NLO in the 3 to 2 jet ratio, you don't really know whether to trust NLO. But now that N and LO is more or less in the same region, you can start to try to use this ratio, which is kind of a measure of alpha S, to measure alpha S much more reliably at a ridiculously large momentum transfer. But mainly this just foreshadows that as these loop amplitudes come online, the N and LO cross sections will come online in pretty short order. So in the last minute, I'll tell you about the dream of planar N equals 4 super Yang-Mills, which is to solve for these scattering amplitudes for arbitrary coupling and for arbitrary kinematics. And we have reasons why we might be able to do this because we understand these boundaries quite well in many cases. And so that's sort of one of the plans for the future on the planar N equals 4 side. We've been able to push perturbatively to 8 loops in a recent very special amplitude or form factor that looks very much like the Higgs amplitude I was mentioning before, but that's just like 6 more loops than you can do in QCD. And you can learn a lot from this. We learned that this thing is dual in some strange way to the 6 gluon amplitude, where this symbol I was mentioning gets reversed. It's very strange. Don't understand it. In the last 20 seconds, I just mentioned that approximations are really mandatory for if you ever want to plot anything at 8 loops, because you have 18 million weight 16 G functions to deal with. So what do? Well, you just do Taylor expansions, and that works great. And this is a case of convergent evolution where phenomenologists realize the same thing, that the sort of differential structure has all the keys you need to evaluate things numerically, even for very complicated elliptic functions. There's also some very novel approximation methods on the horizon that involve something called tropicalization. And in some cases, you can get numerical evaluations of 17 loop integrals done so this needs to be explored for the more complicated types of integrals in collider physics too. There's also machine learning approximations. Jesse mentioned this work earlier. This is a little bit of a follow-up to it. So you can see the prediction of a neural network for a whole distribution here. We've been playing around with whether you could use machine learning exactly. We have 1.6 billion coefficients in a certain 8-loop amplitude, and here's all the statistics here. Before the BSM people get too excited, I want to point out that this is not a peak in a mass distribution. It's a coefficients of, and by the way, it's going away, you see, when you take more statistics, so, oh well. So anyway, I think that these amplitudes, notions, and methods are going to continue to interact strongly with between QCD and amplitudes. I've only touched on a small fraction of the ideas out there, and with the help of them and many other non-amplitudes techniques, we're going to push to higher precision and feed that into the LHC, as well as any other future colliders that come out of the Snowmass process. So I'll just stop there. Thanks.
Okay, thank you. Questions here in the room? Or on Zoom?
There's none on Zoom, but can I abuse my microphone privileges again? So Lance, you mentioned twice an antipodal duality.
Yeah.
Can I just invite you to say a little bit more about that? So I'm out of curiosity.
It's basically, there's a symbol you construct that has a lot of letters in it that characterize the derivatives of function on one end and the branch cuts on the other. And we found this kind of amazing relation that the 6 gluon amplitude, you write its symbol, you have to go on a 2-dimensional surface, so it has the same dimension as this form factor. And then you're instructed to find a map between the 2 phase spaces and then write the symbol backwards. So and often in dualities, things are the same function, reinterpreting the variables. This is some twisted thing where things get totally twisted up. And it's not at all clear what the underlying physics reason is, but we're pretty confident in it because we happen to, those are the 2 things we could calculate to the highest loop order. So it works to 7 loops. And it connects 93 million terms at 7 loops, and everything, works pretty perfectly. So it looks like an all orders thing. We think it might have something to do with the flux tube picture, because some of the kinematic map looks like this flux tube picture, which I didn't have a chance to describe, but it heavily involves quantum integrability.
Great, thank you.
So do you think, is there a chance that this might work also for a leading transcendental piece in QCD? Let's say?
Yeah, also this particular process we're looking at, it's like the most complicated process that seems to have this maximal transcendentality principle holding. Some things with even more scales often don't obey this principle, but this one does at 2 loops, but we don't have a proof that it will at higher loops, but it may give the leading transcendental part of what you need for n cubed LO Higgs plus jet, for example, or n4 LO Higgs total cross section, this piece of it. There's a question in the back.
Question by Dan.
Hi, this is Dan Green. I just had a question about this virtuous circle and machine learning.
Yeah.
So you describe part of the reason that you want to calculate the higher orders is to, unearth structures that will then give you new principles. To what degree does, finding higher order by machine learning help this virtuous circle as opposed to just give you an answer without insight?
Yeah, well, it's a great question. It's a little preliminary for me to try to answer that question. I have been playing with 2 machine learning experts, and just the things that the computer finds hard challenge me to try to, as a human eye, try to figure out what's going on. Let me just say that. So just thinking about what's easy and hard for the computer is lets me think about things I wouldn't have thought of otherwise. But okay, that's just one small thing. I think to the extent that it gives, if it works and gives you higher loops, then you get more data to try to fit everything into an all orders perspective without having to know how the machine got there. We don't know if we can do that yet, though.
Okay, thanks.
Okay, thank you. More questions? If not, let's thank Lance again.